In the last video, you should have learned how to calculate curl. We're going to do another curl example right now, and I saved it for this video because of what it merges into. So I am just going to keep going. So we are now doing curl F for a new vector field, okay? So I have a new vector field, and that vector field is F is 2xy, x squared plus z squared, 2yz. And if I want to find the curl of that vector field, at the point xyz, I'm going to find the determinant of this matrix. Two xy, x squared plus z squared, 2yz. All right, so again, to find curl, we find the determinant of the matrix. So I is going to be multiplied by the, what am I looking for? Like cross the difference of duh to y of 2yz, which is 2z, minus duh to z of x squared plus z squared, which is 2z. Okay, I'm starting with 0 again. That's cool. Minus the j component. Duh to x of 2yz is 0. Duh to z of 2xy, also 0. Cool. And then plus the k component, which is going to be duh to x of x squared plus z squared. Duh to y of 2xy. Hey, it looks like I might have done this on purpose. I did. I now got curl that is the 0 vector, which means how could I stick a paddle wheel in so this thing turns? I can't. Not going to turn. This is what's called irrotational. And it means not only at a certain point does this thing not spin, this was my curl for any point x, y, z. So that means I don't care where you stick a paddle wheel, it is not going to turn if you stick that paddle wheel inside this 3D vector. Okay? So the test for convergence can also rely on curl. Now, we did a test for convergence, a test for conservative fields, pardon me. I don't know why I said convergence. The test for whether a field is conservative or not can also rely on curl. If you have an irrotational vector field, that vector field is conservative. Okay, so if you want to know if a vector field is conservative, the curl will equal 0. Okay, we talked about conservative fields way back up here, scrolling. And we said if I wanted to determine if a 2D field was conservative, I could do dn to x equals dm to y and see if that's true or not. But we never talked about what if it's 3D. Well, now we're going to do that. If I want to know if a 3D field is conservative, I can figure out its curl. And if its curl equals 0, then that 3D field is conservative, which means it does have a potential function. Okay? So technically, there are 2 ways to determine whether a field is conservative. Option 1, you can use the tests. Or there's another option, which I'm going to get to in a second, which is just try to find a potential function. And if you can find one, then it's conservative. So let me show you how that might work down here. So it says determine whether each of the following fields is conservative. So I had x cubed y squared z plus x squared z plus x squared y. I can't even talk. Option 1 is use the test. Since this is 3D, I would want to know if the curl is the 0 vector. Okay, so is that true? Well, let's find out. I'm going to set up my determinant. This part takes forever, which is why when I can, I actually do the second version of testing for whether something is conservative more often than I do this one. Gotta be honest. Okay, so if I want to see if the curl equals 0, I want to evaluate this determinant. And so I is going to be multiplied by duh to y of x squared y, that's x squared, minus duh to z of x squared z, which is x squared. Okay, so far so good. J duh to x of x squared y, 2xy, minus duh to z of x cubed y squared z, 2x cubed, nope, nope, pardon me, duh to z of that is x cubed y squared. Oh, this does not equal 0. Therefore, curl does not equal the 0 vector. Therefore, this is not conservative. All right. Now, let me show you option 2. Option 2 here is just try to find a potential function. So if this vector field is conservative, that means the derivative with respect to x of some potential function is x cubed y squared z. And if I took the antiderivative with respect to x, I'd have 1/4 x to the 4th y squared z plus some constant with respect to x. F sub y, the derivative of the potential function with respect to y, is x squared z. The antiderivative with respect to y would be x squared yz. Is this equal to that, or is it a constant with respect to x? Well, x squared yz is not equal to 1/4 x to the 4th y squared z. And x squared yz is not a constant with respect to x. I cannot find a suitable potential function. Therefore, this is not conservative. So option 1, test whether curl is 0. Option 2, try to find a potential function and see if it works. Okay. In question 2, we already figured out above, up this way, we figured out already that the curl of that does equal the 0 vector. Therefore, it has to be conservative. Therefore, a potential function exists. So now I'm going to try to find the antiderivative. So 2xy would be f sub x for that potential function, making my potential function have a term of x squared y plus some constant with respect to x. F sub y is x squared plus z squared, making the antiderivative with respect to y x squared y plus z squared y. X squared y, totally fine, that matches up. And z squared y is a constant with respect to x. So far I'm good. And my derivative with respect to z is that third component, 2yz, making the antiderivative with respect to z yz squared. I forgot my c sub y here. Okay, is yz squared in something else? It is. And yz squared is a constant, pardon me, isn't a constant with respect to y, but it's already in that y antiderivative. But yz squared is a constant with respect to x, so I'm okay. Which means my potential function is x squared y plus yz squared plus any other random constant c. And if you're not sure if that works or not, you can always take the derivative and see if everything's okay. Is the derivative of that blue thing with respect to x 2xy? Yeah. Is the derivative of the blue thing with respect to y x squared z squared? X squared z squared. Yeah. Is the derivative with respect to z 2yz? 0, 2yz. Yeah. So there's my potential function. And this is my attempt at humor. So if we have a conservative vector field, that's the thing on the left. If you have a liberal vector field, that's your donkeys on the right. Okay, I am done giving you all the information. You will now have a problem set that should be in your assignments tab. So check that thing out, and you guys should be all set. Have an excellent rest of the day, and hopefully this made some sense. I don't know why we're using it yet, but you will at some point.